All right, well, we just went through pretty good little word problem, engineering problem, math problem, algebra problem, whatever you want to call it. But that's going to be a very typical energy technology problem, being able to convert between different types of energy, and then just doing a little bit of simple dimensional analysis, unit analysis, keeping track of units. Another question just came up. What's the format for the exam? If I go into the course, I'll just show you quickly what the exam's going to look like. Week 1, week 2. You can see that I've highlighted week 2, so now it's highlighted with this gray background. Click on the exam. I'm going to need to reopen it. It closed from the previous semester, but it's going to be, well, have you never taken an online exam before, or?
No, I have.
Okay, yeah, it's just radio buttons. You click on it, and then a blank. It's just like filling out any other online form you've ever done before. If there's a save option at the bottom, and I think there will be sure you just save the thing. Don't get to the end like, oh, I forgot to say my answers. Another thing that might be handy, the questions are shuffled. So your problem 1 is not going to be the same as your problem 1, but almost certainly you're going to get the same set of questions on each exam. It could be that you come back and take it a second time. I'm going to give you 2 shots at each exam. Since they're random and since we don't use the entire question bank, you might see 1 or 2 new questions, but probably they'll be the same. Couple different options for saving your work in case you don't trust your internet connection. One thing I'll do, if I'm just sitting here on the screen, I'll do a Control A, which is select all, Control A. And then if I go and just open up like a Microsoft Word or something like this, whatever your favorite editor is. Let's see if mine will behave here. Keep getting this weird behavior of Word. Where the window doesn't actually pop up. Let me close a couple of things. You guys ever get that problem? Where it's set like it
gives me that little icon.
I mean the window. Okay, there we go. So I did a Control A. Now if I just do Control V, actually Control A, Control C for copy, then Control V.
It'll put it on there for we all jump it up.
Well, not too bad. It's legible. You can just copy and paste your work as you go. There's another one that I use sometimes. This might come in handy on my computer. There's a print screen function. So, hey, is that? So if you do the function print screen, another way to just save your work, rather than pasting that into Microsoft Word, I would paste it into something like PowerPoint. Control V, and there's the same information. So you can paste this text into Word. You can paste it as a picture into PowerPoint and just kind of keep saving your work that way, and that way.
Why? I'm a little.
Oh, because you'll be sitting there 2 hours into your 3-hour exam and just rocking it, and then a squirrel will chew through your Ethernet cable at home, and you'll lose all your work, and you'll come complaining to me that you got moodled. I'll say, welcome to the club. We all get. That's the only reason. I mean, there almost certainly will be a save button at the bottom of the screen where you can save your answers as you go in case you get kicked out for whatever reason. So that's just save your work. So if that happens, you've got a copy of it.
So is this going to be multiple choices?
Oh yeah, multiple choice, some short answer, a couple little essays, maybe a true false or so. And then, as I just mentioned, some numerical problems as well. So mostly multiple choice, though. All right, so that's a little preview of the exam, and it's all going to be, well, the vast majority is going to be Chapter 1 and Chapter 2, and then we'll have a couple of numerical problems similar to the one that we just reviewed. Okay, so let's go into the course. And again, I'm just going to hit the highlights. I'm not going to read the text to you, but I just want to make sure that we're all. I think I got to several of these figures last time. We went over what a system was. We went over the price of oil. This is the outline of the book. This is that 10 megajoule, 200 megajoule problem we looked at previously. And again, when we looked at the number of wind turbines per person, we can sort of get a sense of like how many joules per person everybody consumes. As it turns out, when you divide these numbers, each person on planet Earth consumes 200 megajoules per person per day of technological energy. We looked at the breakdown. So that 27.4%, that's a pretty close estimate. Remember, we know that the global energy consumption of 500 exajoules, and we just looked at 137 as coal, so that sounds about right when you kind of put those two numbers together. Talked a little bit about energy security. And I think this is actually a ransom being dropped onto the deck of a boat after it was hijacked.
A couple months or something.
Yeah. Fun.
What was that movie, Captain Phillips or something?
Good show. Even crazier that was true.
Yeah.
Yeah, definitely.
I thought it was crazy that they gave up their hostage before they got Captain Phillips. They both had guns.
Yeah.
Hey, let's do an exchange.
Yeah.
And they gave up the Somali pirate to the guys before they got their captain back, and then they took their guy and the captain and took off in the lifeboat. And I'm like, why would?
Yeah, I don't know.
Why wouldn't you
I don't.
say, give me the captain first, and then you can have your pirate, and you guys can get out of here.
I didn't see the movie, and I'm assuming we're not dealing with 100% rational people either. So.
Oh, you don't think? It seems pretty rational. Small.
So here's a shot of per energy consumption per capita, and this is rated in tons of oil equivalent. So North Americans over 6 tons of oil per year. You can see some less wealthy nations are even a quarter of that. What I didn't mention is North Americans consume about 6 times consume energy at about 6 times the average rate. The average North American consumes energy at about 6 times the average rate of person on the planet Earth. When we did that 10 million to 1 problem, remember we took all of the 3 billion years of energy storage, we're consuming that in about 300 years. You can see that our decision to start at 1850 or 1860 is about right. Now, the other perhaps confusing part about this graph, if you look at the percentage of energy consumption, you can see that renewables, that's going to be almost entirely wood. That green line, that's not how much, that's just what fraction. So you kind of have to take this figure and combine it with this one and realize that that green line, even though it went down, it's still actually going up on an absolute basis. Does that make sense, those two back and forth against each other? And then we'll talk about peak oil later. The question is, are we running out of oil, or are we just using other things instead? And you'll see both sides of the argument on that one. Okay, some more big numbers for you here. 5.4 exajoules per year. 5.4 million exajoules per year. If we run that number really quick, let's do this. So let's look at total solar input, 5.4 times 10 to the 6th exajoules, and let's divide that by 500 exajoules, right? So the question is, could we get all of our energy from the sun or not? Are we above what's called the photosynthetic ceiling? And I guess I closed my Microsoft Excel, but let's dive into that. So, okay, there we go. So equals 5.4 E6 divided by 500. Yeah, 10,000. So, what that tells me is, going back here, well, only about 2/3 of it hits the planet, right? Some of it just gets reflected right back. So you can take that number and knock it down a fair amount. Some of it is converted directly into heat. A very small fraction actually goes into photosynthesis, making new coal, if you will.
Why did you divide that by 500? Where did you get the 500 from?
Oh, on this guy right here, I took the 5.4 million exajoules per year, and I divided it by the 500 exajoules per year. Humanity consumes 500 exajoules per
Oh, okay.
year.
I got
Yeah,
it.
yeah,
All right,
yeah,
thank
yeah,
you.
yeah. So what that tells us is that we've got a safety margin of 10,000, if you will. Like we could boost up our energy consumption by 4 orders of magnitude, and we just wouldn't be using energy faster than it was coming from the sun. But rather than just having like a Montana devoted to wind or a Texas devoted to PV, the entire surface of the planet would be devoted to energy harvesting. And when you hit that, you hit what's called a Kardashev Type 1 society. That was something that was published in the 1960s. Russian scientists said, hey, civilization is using more energy. What's the limit? So that a Type 1 society is one that uses all of the sun's energy. It hits the planet, and then there's another one that uses all the sun's energy, and then you start tapping the galaxy and all that. It's kind of sci-fi, but... So another thing to keep in mind is that, this bit of energy, this little less than 1%, that's still fundamentally solar. All of that energy flowing around is based on thermal gradients that are caused by things getting hot or cold depending on where the sun is shining. Ocean tides, solar or not? No, that's lunar. It's driven by gravity. Yeah, that's driven by gravity. We talked a little bit about hydroelectric. The number is not there, but this is the hydrological cycle. Any water that ended up behind that dam was a raindrop flowing down a stream at one point. So you can see what fraction is there. So there's no energy shortage per se. It's just a matter of where we're getting it from and what the downstream impacts are. And I think, as we'll see, there's no perfect energy system. It's usually a matter of just kind of picking your poison. Okay, so that's big picture. Here are some projections. There's that 500 exajoule magic number. You can see there's a little hump right there, and and we're going to see that in another paper we'll look at later. The question is, are more people living in poverty because they can't afford that energy, or is it that we're becoming more energy efficient, right?
I think the technology is becoming more energy efficient as far as your cell phones may not charge at a higher rate than they did when they first came out.
Could be a little both, yeah. Could be a little bit of both. But we know that in general technologies are becoming more efficient, and we'll talk about that in great detail in Energy 102. So here are a few predictions based on where we might go with future energy supplies. Nobody can predict the future, but that's kind of a business as usual prediction. This is to show you the power of exponential curves. So all we're looking at, when I first started studying this, I was very surprised to hear that a person living in 2010 or 2015 in North America is using 6 times the amount of energy that someone living in 1956 North America was. But it turns out America in 1956 is where the world is now in terms of average energy use. But you can look, even with very modest growth, just 2.5% per year, 5.5% per year, gosh, you can see there's double, triple, quadruple the rate, just with a modest change in interest per year. So that's the kind of the power of the exponential function, if you will. In each one of these figures, the volume or the area under the curve actually doubles. Again, showing the power of the exponential. Okay. Now this guy, this is showing China in the last 30 years, and it's their GDP. A lot of that's coming from manufacturing. And the question is whether or not they will be able to sustain that. We're going to see more of this type of modeling when we get to summary 3 in a couple weeks, because what the 2 lines, one is the data, that's the blue line, and the other one is just a curve, just a model, just something to the e to the x power. And the question becomes, will they be able to sustain that or not? Another very interesting statistic is that it falls almost in lockstep with their coal production. And you can run all the statistics you want, but something like this showing, the more coal we burn, the more metals we can make, the more plastics we can manufacture, the more cars we can build, what have you. It's money and energy are pretty tightly related. No question there. Okay, now another theme that goes throughout this first book, there are a couple different mindsets. The first one that we've just been looking at is the growthist model, the business as usual. Everything can kind of just keep expanding forever. The next one, and I think I find myself more in this category, is what's called the peakist, meaning that at some point something reaches a limit and it just can't go anymore. I mean, just think about how many people you can pack in your car before it's full, or how much straw you can load in your wagon before you bust the wheels, or how many people fit in the swimming pool before nobody else wants to get. The universe is, I shouldn't say the universe, the Earth's fossil fuel energy is finite. So at some point, it's going to peak. And it looks like, from what we've seen, that we might be, in fact, reaching that. Oil, it appears, either has or very shortly will peak. Maybe the same is true with natural gas. It depends on exactly what type of extraction technology you're talking about. Coal, in most people's minds, has not yet peaked. We have not yet burned half the planet's coal. And that's why you see coal sort of playing a more prominent role. The question is, will and should we continue to burn it, and what might the consequences be in terms of atmospheric warming, sea level rise, et cetera, et cetera. Okay, now comes the political parts, because all of these natural resources are under somebody's soil somewhere, and we're looking at regional shares of world's proven oil, natural gas, and coal reserves. So the big black one there, North America, coal, something like 30% of North America's coal is actually within the boundaries of Montana. I just came back from the China, Montana. I mean, right now, Montana is negotiating directly with China in terms of coal sales. I was there in the same room with Baucus and Bullock and probably 200 Chinese, all of whom want to continue to see that GDP improve, but none of whom really want to deal with the pollution. So it was a clean coal conference, And the question is, well, gosh, how clean can the stuff really be? Okay, you can take the mercury out, they gotta fix the acid rain. Can we solve the CO2 problem or not? That's kind of the big pink elephant in the room, if you will. Okay. Here's the next one. This is almost identical to that banking problem where we came out with that 10 million to 1 ratio. This is your reserve to production ratio, and it's just in number of years. This is the number of years left of each of these resources if we keep producing at the same rate that we are now. Obviously, let's just take North America and look at 11 years of natural gas. Like, who's going to believe that? No way, man, we got more than 11 years of natural gas yet left. Well, we'll see. I don't know. I also just went to the Montana Bureau of Economic Research meeting in, gosh, what was that? March of this year, and the horizontal drillers are now starting to drill up. At some point, where do you go? Do you then tap the atmosphere and suck back in some of the methane that's leaking out of the pipe somewhere? I'm just not sure. And you can also see how, and you guys have probably played poker before too, it's usually not in the best interest of the person holding the fattest cards to let everybody know that either. So it's difficult to know how accurate these numbers are, whether they have a purely scientific basis or if there might be a political or economic basis to them as well. Okay, this is a photograph of Russia sticking its flag in the North Pole, and this, is a fairly conventional way that sovereign states claim a stake, literally a stake in new ground. The United States effectively did that when we went to the moon, right? We stuck the American flag right there in the moon, okay, ours, fine. Russia managed to get this robot under the ice cap, stuck their flag in and say, this is our oil. We're going to come up here and drill because we got there first. Sorry. And then I gotta skip ahead to this one. So this is the president of the Maldives sort of thinking that, well, gosh, if you guys keep doing that and burning your fossil fuels, my little country that's only a few meters above sea level is going to be gone when the air warms and the ocean rises. So this is his own little political answer to the figure that we just saw, perhaps. Okay, now we saw energy flows a couple figures ago. This one is, and again, it's a little bit cartoonish. When you take NRGY 242, we're going to dig into these numbers in a lot more detail. I'm on page 22, it's figure 119. These numbers, rather than being in absolute values, they're just in percentages. So you start here with 100, and that's that 5.4 million exajoules per year. That's your 100. Another way of thinking that this is a normalized number. You could also put that number as 1. So you can think of it in a range between 0 and 1. In this case, it's just kind of easier to think of it in terms of number between 0 and 100. So again, there's that 30% bouncing back just off the atmosphere, combined with what bounces back off the Earth's surface. Some of it is just absorbed directly. So first law of thermodynamics, energy cannot be created or destroyed. Those photons hit the ground, and everyone knows what happens. Just go stick your hand out on the pavement or the dirt. It gets hot. The energy goes somewhere. Some of it just stays in the atmosphere. So it's not that easy to wrap your head around, but the atmosphere is transparent to some wavelengths of radiation, and it's opaque to others. So the atmosphere is actually transparent to 20% of all the photons that hit it, and then the photons just kind of stick around and stay there. Now, where does the heat go? So of this energy that's kind of here in the atmosphere, again, that matter radiates as well. some of it radiates back into space, some of it kind of bounces around and has a second chance and gets absorbed by the surface of the Earth. Some of that radiates right back into space. The Earth is warmer than outer space, obviously. It's 3.7 Kelvin in outer space, so here it goes, radiating back. The universe is always trying to look towards thermodynamic equilibrium. This is the part, this is the sort of the contentious part, and this is the part that's driven by chemistry. When we get into NRG 102, we'll dig into this a little bit deeper and understand exactly why this radiation that otherwise would have escaped into space sort of sticks around. And it all has to do with how transparent or opaque different wavelengths of radiation are to different things in the atmosphere. Methane, water, CO2 being among them. So those are just kind of the big numbers to keep in the back of your mind. All right. If you watched Al Gore's movie, you probably saw this. He went and stood on his ladder to, get to the, the levels of CO2. You might say, well, gosh, this isn't really a fair basis. I mean, zero's down here somewhere. It's just some kind of little blip in the data. But this data is the culmination of worldwide deployed sensors. There's sensors all over the planet now. In fact, a couple of professors here at the university just won the X Prize for sensors that they're deploying in the ocean to measure acidity and CO2 absorption. So kind of hard to argue with this data. Here's the 95% confidence range, and you can think about that in the same way we did with those significant digits on the problems a second ago, is how confident you are. Well, it might not be 3.5, et cetera, but okay, it's 3.5. We can agree at that. That's how to think of that. So this, so the bottom is just the temperature of the atmosphere creeping up, and I have a little example of that in my summary 1 paper that we're going to see. Okay, we've seen the Maldives. So this would be a way to move forward and sort of starting to take the fossil fuels out of the equation. So you can sort of see these guys getting pinched. You can see biomass expanding. You might think of biomass as a carbon neutral source. The trees are taking the CO2 out of the atmosphere. You burn them and it goes back in, but it's sort of sustainable in that sense. You're not taking old carbon out of the ground and putting it in the atmosphere. And then nuclear comes online too, because it's roughly carbon neutral. Nothing's really being set on fire in a nuclear reactor. Okay, here are a few examples of environmental disasters, problems. I think we've all seen those before. And then this is, it's kind of a neat way to think about the peakest and the growthest. Somebody I heard earlier say, yeah, I'm just going to go back to burning candles. Well, you might find yourself in the environmentalist standpoint, right? So, but I think, really the place to be, and that's fine. I mean, there might be people like, hey, I'm going to go off and do the survivor thing for real. I'm going to go Kaczynski or whatever. You might have people that are living in their little growthist fantasy as well, and they're going to come up against limits or not. And then, like I said, I tend to fall into this peakist category, but I think through this course we can see the points of all three. And this is kind of where you get into that triple bottom line mentality where, we want to get richer, we want to be happy, but we don't want to screw up the planet doing it. That's that kind of middle ground, that triple bottom line you've probably heard about before. All right. Do take a look at that box 1.7. It's called the Kaya identity. And in a lot of ways, what it's saying is like, the more energy you use, the happier you are. But if your happiness results in the malady of others, like the poor president of the Maldives underwater, maybe that's not the best way forward. And that's what the Kaya identity is all about. Okay. And then, I always find this to be fascinating, to show how much further we either need to, or have to, or feel compelled to drive. And this is just the UK. It's always sad to see the pedal cycle on the downturn, but oh well. Looks like rail might be on the rise a little bit in the UK.
They just don't have a lot of space to put.
It's kind of surprising, though. I mean, you'd almost think that rail would become more prevalent, but man, they're just, yeah.
Other parts of Europe it is, but
Yeah.
hey, it's so heavily populated, no growth already, and there's no need for train.
Yeah, it's surprising. Okay, well, that's pretty good timing. That was the last figure in chapter 1. Thursday, we will go through chapter 2, so please just read up on that. We'll just kind of sweep through the whole thing, and then I'll have you ready for the exam. I'll launch the exam at 2:30 on Thursday, and I'll give you through the following Tuesday to finish it. Sound good? Okay, guys, thanks.
Have you seen the YouTube video on the solar roadway?
Oh,
They create little octagon, like cells.
I have heard of those, yeah. Seems like a pretty good use of space. I'd love to see the Bitterroot branch turn into a solar pathway too, just PV the whole thing.
Their estimations was if you covered every paved road in America, that's already paved,
Yeah.
not stone roads,
Yeah.
with this stuff, it would produce 3 times the amount of energy that we use.
That sounds about right, yeah, that sounds about right.
Yeah, but they don't have any cost numbers on how much it would cost
Right.
because it's not an actual product.
Right, yeah, there's
Not a prototype.
there's a couple trails, I think, I want to say in maybe Copenhagen that have been experimenting that, not with vehicle traffic, but more pathways. Take care, see ya.
But they have LED lights in them, they can change lanes. It says you can also check, like if there's a moose crossing the road,
Oh, yeah.
you can flash lights ahead saying, hey, there's something in the road.
Oh, radical.
You don't have to plow it because it creates, some heat.
Oh, sure,
The
yeah.
snow never accumulates.
Yep.
Apparently they did it to, whoever it was, a husband and wife, professors or doctors or whatever,
Yeah.
they came up with it, and they did it to a section of their driveway.
Oh, nice,
It's
okay.
like a prototype.
Yeah,
It's a neat idea, but
gotta start somewhere,
you
yeah.
have to rip up all the roads in America and put a big, access tunnel for all your wiring and all your stuff.
Well, it's funny, it's probably a similar argument was used about the subway in New York City, like, how are you gonna get a tube underground? But,
They found a way to do
yeah.
it.
Okay, guys, see you Thursday, thanks.
You meet at 3?
What's that?
You meet at 3?
3102? Yeah.
Okay.
Yeah.
Sorry for storming into your class.
Oh, it's okay.